So continuation with morning class, where we have discussed about the physical properties of water and also the ionization of water. Then we discussed about the three theories of acid bases, that is Arrhenius theory, Bronsted-Lowry theory, and Lewis theory. Then we discussed about the what are strong acids and strong bases, and we also explained about the what is the relationship between the strength of acid and Ka and pKa. Finally, I have concluded that strong acids have the higher Ka values and lower pKa values, whereas weak acid has lower Ka and higher pKa. So you should remember that in the examination point of view, if you come across Ka and pKa, you should understand that strong acids have higher Ka because they have the equilibrium towards right, so they dissociate completely in water, whereas weak acids have equilibria towards left, they dissociate partially in water. So therefore, strong acids have higher Ka, whereas weak acids have lower Ka. That is the acid dissociation constant. So now to understand this one, you may expect some numericals in the exam. I will just give two numericals. I think you will be able to understand. Butanoic acid. Butanoic acid. The substance responsible for the odor of rancid butter. Rancid butter has pKa 4.82. What is its Ka? So that means it is already, we know that pKa is equal to minus log Ka. So now pK is already given, that is 4.82. That is equal to minus log Ka. So using a calculator, you need to do this one. So log Ka is equal to minus 4.82. Therefore, Ka is equal to anti-log minus 4.82. That is equal to, it comes from, if you I think if you have calcium, you can do this one. So that is the Ka value. I think it will come in 1.51 into 10 to the power minus 5. So like this, you need to, if the K is given, you need to calculate the pK. If the pK is given, you can also able to calculate the other values. And in the same way, second numerical, that is formic acid, HCOOH. Formic acid has pKa value 3.75, whereas picric acid has pKa value 0.38. What is the K of each? What is the Ka of each? So you need to do this one. Then number 2, so same thing, same way as I already explained previously, same way you can do this one. And second, in the same problem, which is stronger? Which is stronger, either formic acid or picric acid. So, we know. So we need not for this. We need not do any calculation, as we already said that higher Ka, lower pKa is strong acid, or lower Ka, higher pKa is weak. So here it is 3.75. It is 0.38. So picric acid has 0.38 pK value, and pK of formic acid has 3.75. Obviously, pK is smaller, so therefore it is stronger. The picric acid is a stronger acid compared to the formic acid. So this is the other way you need to understand this numerical. And I think with this, I think you will be able to understand any numerical that comes based on the pKa and Ka. And coming to the next, we have, according to the syllabus, we have the definition of pH and pOH. So we know that this is not the chemistry subject, but anyhow we can refresh what is pH and what is pOH. And pH is the way to the express the hydrogen ion concentration of a solution. So therefore, the pH is equal to negative logarithm of hydrogen ion concentration or hydrogen ion activity, and therefore pH is equal to minus log H plus, that is equal to log 1 by H plus. So the solutions that are having the pH less than 7, they are known as acidic solutions. If they have the greater than 7, they are basic solutions. And then coming to the pOH, it is the negative logarithm of hydrogen ion activity, and the pOH is equal to minus log OH minus ion concentration, that is equal to log 1 by OH minus ion concentration. So that means pH is equal to minus log H plus and pOH is equal to minus log OH minus. And now the relationship between pH and pOH, we know from the previous, from the morning, we have already explained about the ionic product of water, that is Kw is equal to concentration of H plus and the concentration of OH minus. So from this we can understand the relationship between the pH and pOH, and when we take the logarithm value here, so it becomes it is a log a into b, it is a log a plus log b, it becomes so when you apply the logarithm here, it becomes log H plus and plus log OH minus is equal to log Kw. So we know when we when we take a negative when we apply a negative sign, minus log H plus becomes pH, minus log OH minus becomes pOH, and minus log Kw is nothing but the pKw. So therefore pH plus pOH is equal to pKw. pH plus pOH is equal to pKw. And as I said that in pure water, the ionic product of Kw is equal to 1 into 10 to the power minus 14. So because the H plus ion concentration is 10 to the power minus 7 and OH minus ion concentration is also 10 to the power minus 7, and therefore the Kw is equal to 1 into 10 to the power minus 14. So therefore, if the Kw is equal to 1 into 10 to the power minus 14, pKw is equal to 14, and that is minus log 10 to the power minus 14, it becomes 14. So therefore, pH plus pOH is equal to 14. That means if you know the pH and you can calculate the pOH by using this the relation, then if you know the pOH, and you can also calculate the pH of the solution. So this is about this one. Now coming to the Henderson-Hasselbalch equation, and before Henderson-Hasselbalch equation, I think we need to we just want to give you the overview of buffer. And I think this Henderson has before this equation, I think we need to understand the buffers. So we know buffers are the solutions which can resist pH change when small amount of acid or base is added. And these buffer solutions are usually consist of a mixture of weak acid and it's a salt with a strong base. And there are two types of buffers. One is acidic buffers, second one is basic buffers. So acidic buffers are composed of the weak acid and its salt with a strong base, whereas the basic buffers composed of weak base and its salt with strong acid. And we know here, for example, you can see here, this is the weak acid, acetic acid, and its salt, sodium acetate. In the same way, carbonic acid and sodium NaHCO3 and NaH2PO4 and Na2HPO4. All these are weak acid and they are the salts. And of course, these buffers are used in biochemistry for studying the for doing the various experiments, and especially the for protein purification or the and various protein related studies. We use the buffers. And coming to the buffer capacity. So buffer capacity is nothing but it is the ability of the buffer to withstand pH change when we add small amount of acid or the when the base is added. So this buffer capacity increases with increasing the ionic strength of the buffer. In the sense, for example, if we have any buffer 0.1 molar, 0.2 molar, or 0.5 molar, so with increasing the ionic strength of the buffer capacity also increases. So that is known as the buffer capacity. And as I already said that there are the different buffers. These they are mainly classified into acidic buffers and the basic buffers. And the acidic buffers, as I said, that they are composed of weak acid, and it's salt with a strong base. For example, acetic acid and sodium acetate are the H2CO3 and NaHCO3, H3PO4 and NaH2PO4, and HCOOH and HCONA. So weak acid and it's a salt with the strong base. And coming to the basic buffers, these basic buffers are composed of the weak base and it's a salt with a strong acid. So for example here, the NH4OH and NH4Cl, NH3 and NH4Cl, and NH3, NH4CO3, all these are the examples for the basic buffers. And last one is there are some double salt buffers. In the sense here we use two salts. For example, is the phosphate buffer. The phosphate buffer we commonly mostly use in every the biochemistry lab or in laboratories. And this phosphate buffer is composed of NaH2PO4 and Na2HPO4, monosodium dihydrogen phosphate, disodium monohydrogen phosphate. These two salts are used to prepare this phosphate buffer. And we will explain the mechanism of some buffers later. And before going to that, these buffers, they have some especially the buffers when we use, they should have certain requirement or the certain characteristics. In the sense, the buffers, the buffer components what we use, they should have the higher solubility. In the sense, they should freely soluble in water. So that means they should have the higher solubility, and they should have higher solubility in the water, and also they should have the minimal solubility in the organic solvent. And second important requirement is that the buffer component should not permeate into the cell membranes. In the sense, when we are doing any assay, or when we are using the biological assay where we are using any cells or the cell lines, the buffers components should not permeate into the membranes. And then third one is the ionic strength. So the ionic strength of the buffer components should not alter the ionic strength of the system. So in the sense, when we take any buffer, the components that are present in the buffer solution should not alter the ionic strength of the system. Then the pKa values of the biological buffers should reside between 6 to 8. So that is they should have the pK values between 6 to 8, and then they should not interfere. They should not form any complex with any metal ions and so on. Then, and another thing is, they should not interfere with any biological process that takes place, and they should not finally absorb the light either in the UV or the visible region. And so these are some of the requirements for the biological buffers. I think in a short form we have given here. So they should have the higher solubility in the water, minimal solubility in the organic solvent. They should not permeate through the biological membranes. Their pK values should reside between the 6 to 8, and then they should not interact with any metals and should not form any complexes. They should not absorb light in the UV region, and they should be non-toxic to the cells. They should not exhibit any toxicity to the cells, and of course they should also be available in pure form, and so on. So these are the requirements or the characteristics of a biological buffers. Then coming to this, in order to prepare any buffer solution, and buffer solution, we use Henderson-Hasselbalch equation. So the Henderson equation, I think it is given here. The Henderson-Hasselbalch equation is Henderson-Hasselbalch equation is pH is equal to pKa plus log concentration of salt by concentration of acid. This is the Henderson-Hasselbalch equation, and this Henderson-Hasselbalch equation is derived by taking the weak acid dissociation, and you can just see here. So when this HH equation is derived by considering the weak acid dissociation. So we know HH equation is pH is equal to pKa plus log concentration of salt divided by concentration of acid, or it is the conjugate base by acid. So this equation is useful to predict the behavior of this equation, or the Henderson-Hasselbalch equation is used to predict the behavior of buffer, and it is also useful to determine the pKa values. This equation is also useful to determine the pKa values in titration curves. This we have already explained when I explained about the amino acid titration curve. Then in addition to this, it is also used to know the ratio of salt and acid for making buffer solution. That means we can understand the behavior of the buffer. We can determine the pK values of weak acid in a titration curve, and we can also we can also determine the ratio of the salt and the acid that is required for making any buffer of desired pH. So therefore the basis for this equation is that the weak acid dissociation. So in the sense, when we weak acid, let us consider weak acid HA, when it dissociates into H plus and A minus, HA aqueous, H plus aqueous in water, and dissociates into the HA dissociates into H plus and A minus, and the dissociation constant for this weak acid or the acidity constant K is equal to concentration of H plus, concentration of A minus divided by concentration of HA. So now from this, when we do the rearrange this one, we get Ka into concentration of HA is equal to H plus and A minus, H plus and A minus. So now from this we can take H plus is equal to H plus, concentration of H plus is equal to Ka, concentration of HA divided by A minus. So to this concentration of A minus. So by applying negative logarithm on both sides, by applying negative log on both sides, we get minus log H plus is equal to minus log Ka, concentration of HA by A minus. So now let me put it here itself. So now we know minus log H plus is nothing but minus log H plus is nothing but pH is equal to minus log K is nothing but pKa. So of course this we can also expand minus log Ka HA is equal to minus log Ka minus log HA by A minus. Therefore minus log Ka becomes pKa and minus log HA, concentration of HA by A minus. So if we remove this negative sign, pH is equal to pKa plus log A minus, concentration of A minus by HA, and this we can also write it as pH is equal to pKa plus log conjugate base, concentration of conjugate base by acid, or we can also write it as pH is equal to pKa plus log salt, concentration of salt by concentration of acid, or still we can also write as pH is equal to pK plus log proton donor by proton acceptor. So in the sense, the many ways we can write these Henderson-Hasselbalch, represent this Henderson-Hasselbalch equation. So this is the Henderson-Hasselbalch equation. So pH is equal to pKa plus log concentration of salt divided by concentration of acid. So that means this equation is useful to predict the behavior of the buffer and to determine the pK values of any weak acid in a titration curve. and we can also determine how much of conjugate base and acid should be mixed in order to make any buffer solution of a desired pH, because pK is a constant for any acid. So that's why this Anderson-Hasselbalch equation is used to determine the to mainly it is used to prepare the any buffer solution and so on. So now we will see we will do one numerical based on the Anderson-Hasselbalch equation. Or let me give some good example, good numerical for this Anderson-Hasselbalch equation. That is the pKa of the pKa are let me give this simple. Yeah. So calculate the pH of a buffer composed of 0.1 molar acetic acid and 0.6 molar sodium acetate. That means HClCO sodium acetate. So as when sodium acetate dissociates, it becomes its conjugate base. Sodium acetate, knowing that the acid dissociation constant, knowing that the acid dissociation constant Ka is 1.8 into 10 to the power of -5. So calculate the pH. So that means, let me make it is simple. Let us say you have here acetate buffer. It has 0.6 molar sodium acetate and 0.1 molar acetic acid, and the Ka value is already given weak acid Ka is 1.8 into 10 to the power of minus 5. So what is the pH of this solution? So that means acetic acid concentration is given and the sodium acetate concentration is also given. So you need to determine the pH of the solution. So this is the acetate buffer in the sense acetate buffer is composed of acetic acid plus sodium acetate. Acetate buffer is prepared weak acid, acetic acid, and it's a salt with a strong base, that is sodium acetate. It is the salt. So now we have, this is a 0.1 molar and this is 0.6 molar, and when we take the when we have the 0.1 molar of acetic acid in the solution and 0.6 molar of this one, and what is the pH of the solution, and the K is already given 1.8 into 10 to the power of minus 5. So what you need to do is you need to do the calculation by applying the using the Henderson-Haber equation, that is pH is equal to pKa plus log A minus by HA. So first what you need to do is that first the Ka is given. Ka is given. First you need to find out pKa. So pKa is equal to minus log Ka. So therefore, you need to first find out the pK value. K is given, but you need to find out the pK value. So the pK, when you do this calculation, you get the pK value is 4.76. When you do the minus log Ka, when you see the logarithm of this one, you will get the 4.774. 4.74. This is the pK value of this one. So now pH is equal to pKa plus log A minus by HA. So we know pH is equal to 4.74 plus log 0.6 divided by, that is A minus, this is a salt, divided by 0.1 molar. So when you take this one using, when you do calculate using a calculator, you will get 4.76, sorry, 74 plus 0.778, that is equal to 5.51. So that means in a buffer solution, if you have 0.1 molar acetic acid and 0.6 molar sodium acetate, the pH of the solution of the acetate buffer solution is 5.51. So this is one model, and then coming to and we can also understand Henderson-Haber equation can also be used to understand the behavior of the drugs when they metabolize in the body. So for that, I will just give you one more numerical. Yeah. So this is again another numerical here. If the pKa for acetyl salicylic acid, acid to acetyl salicylate, acetyl salicylate is 3.5. Is aspirin a weak or strong acid? Is aspirin a weak or a strong acid? Which form is predominant in stomach at a pH of 1? At a pH of 1. Which form is predominant in blood at pH of 7.4? Prove this using HH equation. So this is the numerical, and what is given here is that this is aspirin, as we already said, that is a non-steroidal anti-inflammatory drug. So that is nothing but acetyl. So this is the COOH. This is O single bond C double bond O single bond CH3. So this is aspirin. So that's still salicylic acid, and its ionized form. Its ionized form is COO minus acetyl salicylate. So that means this is HA and this is A minus acetyl salicylate. It is the conjugate base. So now we wanted to know that when we take aspirin and when it enters into the stomach, which form is predominant, whether it exists in its protonated form or the acetyl salicylate form at a pH 1, and which form is predominant at a pH 7.4. So for this one, you need to prove using the HH equation. And this, I think here the pKa is not given. Sorry, it is already pKa is given 3.5. So now what we need to do here, so totally what we need to find out, pH 1, which form is predominant, this or this? At a pH 7.4, which form is predominant? First we will start in stomach first. stomach where the pH is 1. So according to the statement. So we need to apply the Henderson-Hasselbalch equation here. pH is equal to pKa plus log A minus divided by HA. Or we can also say that this is the salt and this is the acid. And pH already given 1. 1 is equal to 3.5 plus log A minus by HA. A minus by HA. So now log A minus by HA is equal to 1 minus 3.5, that is equal to minus 2.5. So A minus by log A minus by HA is equal to minus 2.5. A minus by A minus by HA is equal to antilog of minus 2.5. So that gives 316.22. So that means A minus by concentration of A minus by HA is equal to 316.22. So that means A minus by HA is equal to 316.22, means for every 1 molecule of HA or 1 mole of HA, 360.2 moles of A minus is present. So that means from this we can understand that the here for every this one so from this we can understand that for every 1 mole of this this is present this many moles. So this form is predominant here. And now coming to, sorry, I think not this form. I think we have done some mistake in the calculation. I think this is M minus by HA is not this one. So 1 minute, I think this is just this one. So A minus by log salt by acid is equal to 1 minus 3.5, that is equal to minus 2.5. So here acid, concentration of acid by salt, or as a concentration of acid by salt by acid is equal to, I think a log value is something wrong. I think this I will just check in the calculator when we will see in the tomorrow's class. I think the anti-log value is not I think correct. I will just check and let you know in tomorrow's class.